Okay, straight from mainland South Korea, another Aims inverter. This is a digital DSP driver, pure sine wave DC to AC inverter. Haven't even opened it up yet. Can't wait to see what they're doing to make this thing a pure sine wave inverter. And I've got the main box opened up, and there is a secondary box inside the main box. So let's get that one opened up as well. So we got a little CAT scan and a little lab work going on here, although it's not a lab in the original box. But according to this, it's a PWRINV5048W and it claims to be a digital signal processor driver pure sine wave inverter. But let me show you what's in the box. So this is what I got out of the box. This is just a PWRINV5048W. That's a stepped square wave inverter. You've seen me repair these in the past. Just a regular old stepped square wave inverter. Just like you've seen several times before. Okay, got it out of the box, got it opened up. Just want to do a quick visual inspection. And unfortunately, this is all the farther that these leads right here will allow me to open this thing up. So I'm going to go ahead and disconnect these leads, unplug these plugs that are pulled tight right now. At least this one's very tight. And we'll do some ohm checks. We'll check all the fuses and see if any of those are blown. And then we'll just do a quick visual look around. I already see something I don't like, and it's this coil right here. It looks like it's been running very, very hot. And so that is what takes the 48 volts and regulates it down to 5 volts for the microprocessor. So hopefully we don't have a coil problem. I can probably rewind that toroidal transformer if I need to. It's just an inductor. That's all it is. It only has one winding on it. So let's go ahead and separate these two halves. I'll need to go ahead and disconnect the upper half from the lower half right here on the positive and negative leads, which are down here. And then we'll test each side separately. I don't like to apply power to these things until I've done a complete, at least look around and test and see what things look like. Okay, so first thing I want to check is all 8 fuses on the master board. When I say master, they call this the master board. The one on the other side is the slave board. That one does not have the microprocessor on it. So let's start. These are all 10 amp fuses because this is a 48 volt inverter. And that one is open. That one's good. That one is open. That one is open. That one's open because it has a negative voltage and it charged, because it's charging capacitors. That one is open. That one is open. And that one is open. So we have 1 good fuse and 7 blown fuses on this side. So that's not looking good for this customer. So next, let's get the slave board out and check the fuses on it as well. Okay, on to the slave board. Open. Good. Open. 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 Good. And open. So we have 2 good fuses on the slave board and 1 good fuse on the master board. I do not have high hopes for this unit. I'm betting we have a bunch of shorted FETs on this thing. It might have been connected backwards. So I think I'll start with the master board. We'll go ahead and pull it apart. Check the FETs individually. May have to unsolder them and see what's going on with them. And yeah, just my expectations have been lowered quite a bit. Out of 16 fuses, I have 3 good ones. So that means 13 blown fuses. So these things are pretty easy to disassemble in reality. It's got 4 screws that hold these bars to press the MOSFETs against the thermal insulator and then against the aluminum heatsink right here. 4 on that side. 4 over here on this side, and then 2 right here, and 1 ground screw over here that might be kind of hard to see for that 1 ground wire. And then once you remove all 11 screws, you can actually very gently pry the MOSFETs off of the thermal pads, and then the whole board will slide out of the unit. Okay, I've got all the braces out. Even the ground screw over here has been removed. So next, I should be able to actually just gently push the circuit board out this way. And then I'll go ahead and pull the case back at the same time. And that gives me access to the full circuit board. Okay, so next I just want to go ahead and check for shorts between drain and source. So these are where the fuses live. Open. Remember, 1 was good. I think it's that one. That one is good. So we'll go ahead and check these first. No short. No short. Now all these had blown fuses. Short. 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 Now over to this side. Short. 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 Another short. Another short. Another short. And another short. So I think at a minimum we need to pull every FET out of this unit and test it. But let's test the output FETs and see if they have any shorts also. And those live right here. Short. That one tests good. That one tests good. And that one tests good. Just for shorts, that's all I'm looking for at this point. Is that one's got a dead short. And that could conceivably short every FET on this board. And I'm expecting to see the exact same scenario on the other side. Okay, so on to the slave side. Same exact thing. 1, 2, 3, 4 screws. 1 here, 1 here, 1, 2, 3, 4. We can move the FETs off of the thermal pads and then slide the board completely out of the unit. Okay, I've got all the FETs loose. And just go ahead and give this a gentle tug forward and backwards and make sure the thermal pads do not move with the FETs. Once you're sure you're clear, you can go ahead and slide the 2 halves apart just like that. Okay, same thing with this one. So that's one of the good fuses. Not shorted. Not shorted. And the other, nope, that one's bad. Bad. That one's a good fuse. Not shorted. And not shorted. We'll test all the other ones. Short. 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 And that was a good one. That's a good one. And short. And short. And on to the output FETs. Once again, only looking for shorts between the drain and the source. That one's not shorted. Not shorted. That one is shorted. And that one is not shorted. So I'd say that we definitely have one FET on the output FETs on each side that are shorted, and a multitude of driver FETs in each of the step up transformers. Their job is to take the 48 volts and step it up so it can do its stepped sine wave via these output FETs on this board and the other 4 output FETs on the other board. So keep in mind, we've got these driver transistors right here, 4 of them right there. We got to check those. We need to check each one of these gate drive resistors. I believe they're 10 ohms each, to make sure that none of these are shorted. So there's going to be 16 on this side and 16 on the other side as well. And since we have a shorted output FET, we want to check these little 1N 4148 diodes, as well as I believe these are 10 ohm resistors. There's one set for each FET. These are the output FET drivers. We want to make sure we test all those, that they're all okay. So just as a preliminary estimate, I'm going to recommend that we replace all 32 of the driver FETs on both boards, as well as all 8 of the output FETs. And I'm going to go ahead and just throw in some miscellaneous charges, just in case we have some defective driver transistors here, and the driver transistors that drive the output FETs on both boards. Plus, all 16 fuses, because even though we have 3 good ones, I'm sure they've been stressed. And there are 4 diodes for each section on this unit. You can see them right here: D29, D25, D30, and D26 right there. I need to check those and make sure none of those diodes are shorted. I don't think they are, because a bad output FET probably won't kill one of these diodes. They're pretty much overrated, but I want to go ahead and check those anyhow. So these can be done very quickly just with the diode ohm check. If I get a beep, it's shorted. If I get a short beep, it's good. 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 And we'll do the whole rest of the unit. Okay, every one of those tests perfectly fine. I'm very happy with that. I'm going to do the other ones on the master board and make sure they're all fine as well. Okay, all those check perfectly fine. Okay, so I want to go ahead and pull a bunch of the fuses out, but look what I found when I pulled the fuses out. Look at those connectors. They've been arcing together. There's another one of the fuse holders. These things have been arcing together. Look at that. Same thing on that one. They're definitely burned up in the center. That last one is the exact same way. Now this side doesn't look too bad. At least that one doesn't look bad. That has not been arcing. That one looks pretty good as well. Not too terribly bad on that one. Unfortunately, that's all the light I can give you right now. But there has been some heavy duty arcing going on in here to melt those fuse holder contacts like that. I'm sorry about the focus. That thing is absolute toast. So what I've done is I went ahead and I pulled all 8 fuses out of this unit. And I went ahead and pulled the 2 FETs out of this one channel right here. I'm going to go ahead and put a fuse in right here, a good fuse, and supply it with 48 volts and see if I can get the system control to even light up, to even come on. Because if I can't, this thing is toast. There's nothing I can do. It's going to have so much damage because of arcing. Maybe a lightning strike. Maybe somebody tried to put 120. I don't know. There's so many possibilities that could be going on. My mind is just trying to scramble to figure out what happened to this thing. So let's go ahead and put a good fuse back in this one slot with no FETs in it. That's going to supply power up here to this regulator IC right here that's going to convert the 48 volts to 5 volts so that the microprocessor that lives right up here in the display board can actually try to power up. So let's see what happens. Okay, so I do have 49.67 volts applied to this unit. I can probably get it down to exactly 48. That's pretty doggone close. So let's go ahead and power this thing up and see if we get anything in this indication right here. This is the battery voltage indicator right here. And look at that, I do get an LED. That tells me that this thing is trying to work. The system control is getting voltage. If I dial this down, I should get a low battery beep sometime in here. And look at that. Bringing it up once again. Bringing it down. So there's 41 volts. Where's the switch at? So at 44 volts, it goes up to the second indicator. And at 46, it goes to the third. So the system control is actually working in this unit. And then at about 41 volts is when I get the low battery indicator. Well, that is a very good sign. That means the system control is working, and this little regulator right here and that coil is actually doing its job. Regardless of how hot it's been, it's actually working. So I'm going to go ahead and give the customer an estimate to replace 32 FETs right here on both boards, as well as 8 of the output FETs. And I mentioned this before, possibly I'm going to go ahead and add a few extra dollars of buffer zone to replace the 8 drivers on this board as well as the 8 drivers on the other board. And we might need to go ahead and change these 4 drivers on this board as well as the 4 on the other board. So there is a possibility you will see a part 2 to this. I'm not sure. Depends on what the part cost is and whether the customer approves the estimate or not. Okay, so I thought I'd go ahead and drag the oscilloscope out. Well, not really drag it out, it's on my bench all the time, but go ahead and show you the waveform. So this is the gate drive to both of the FETs that I have removed. And this is just basically an integrity check to make sure that the microprocessor is actually trying to control the FETs. And as you can see, it's oscillating at 45 kilohertz, almost exactly. I've got 12.2 volts peak to peak. And the waveform looks great. These FETs should be switching on and off. So the top waveform is on one of the 2 FETs. The bottom waveform is on the other FET. So you can see how they kind of alternate. One on, then off. Then the other one, then off. And so that's what I wanted to see. That tells me that the driver transistors on at least this one channel are working okay. I can't say anything for the other channel. Let me go ahead and move the scope probes and we'll see if we get anything on the other side. There still could be other damage. There is how I have the probe situated right now. The gate of Q6 and the gate of Q5, the 2 FETs that I removed from the circuit. So I'm going to go ahead and move these over to the other side. I have not removed any of these FETs, but we'll just see if we get any waveform over there as well. And I'm not seeing a waveform on the lower trace, but I am seeing a waveform on the upper trace. And now that might be because of the shorted FETs. I have not removed these FETs from the circuit. Let's go ahead and look at the drive side of the FETs, which is right there. And I see a perfect waveform. I'm totally happy with that. I think this thing might actually be savable. As you can see, I'm checking on the input side of the 10 ohm resistors, and especially on this one, if I move it to the output side, my waveform goes to 0. So that's the drive side, and that is the FET side. Very happy to see that. I think this thing might actually be salvageable. I thought I'd give you a close-up view of one of the fuses that was melted. Look at that, it melted the plastic because of the arcing. But take a look at this. This is an ATU fuse rated at 32 volts. This is a 48 volt inverter. How did they get away with using these things? This thing cannot possibly be Underwriters Laboratory approved or CSA approved with a 32 volt and a 48 volt application. But I just thought I'd show you the condition of the fuse after the arcing incident. Not looking good. I certainly hope you enjoyed the troubleshooting portion of this video on the Aims PWRINV5048W. Go ahead and leave me a question, a comment, a concern down below, good or bad. I try to respond to the comments when I have time. While you're down there, hit that subscribe button and like this video. It really does help my channel grow. You can follow me on social media, Facebook, Instagram, Twitter at NorCal715. You can email me norcal715videos@gmail.com. If you do message me on Facebook, Instagram, or Twitter, please be aware it might be weeks or even months before I respond. I rarely check those for messages. Please, if you want to contact me, use the Gmail address. Remember, with your help, we can try, and I emphasize try, to keep these things out of the landfill, out of the recycle bin, and out of the e-waste facility. Everyone, thank you for making it to the end of this troubleshooting video, possibly one of one or one of two. We'll see what happens. Thanks so much for watching. I really do appreciate it. Bye-bye. Okay, a little bonus material. Check out these connectors. This is one of the two fuse receptacles, which is just basically 2/4 inch lugs. But check out that carnage on that thing. Hopefully it'll stay in focus. Look at how much molten metal there is on those connectors. It is absolutely toast. I'm just going to have to unsolder those and replace them if the customer actually approves the estimate. So by comparison, let's look at the other channel, which is right over here. Right there. That's how they should look. Those look absolutely perfect. So there's your before and after shots right there. Wow. And so this is the slave side that I have opened up right now. And I'm just getting ready to put it back together and set it aside until the customer either approves or declines the estimate. Got it just loosely in the chassis here, which is what I normally do. I'm not even going to put thermal pads back in. I've got them in a Ziploc bag. But let me get the micro zoom back on here. Yeah, here's one of the fuses. Look at the carnage on that thing. It actually welded part of the receptacle to the fuse leg itself. That's how much power was induced in this thing. It welded itself back together. Look at that. Quite amazing. Anyhow, just a bit of bonus material. Look at the arcing on that thing too. Well, if you want to know how to weld some metal, there you go. 48 volts and quite a bit of current, I'd say, to get this job done. Anyhow, thanks for watching. Have a great day. Bye-bye.